Hey, how y'all doing today? So
Doing good.
like
How are you doing today?
doing okay. I'm glad you answered because otherwise it'd be like talking into the void. Sometimes that's how it feels. Zoom is great in some ways, and then in other ways, not so much. Okay, so where we're standing here is not quite done with well, the term, not even quite halfway done, but yeah, 40%, so that's good. Where I stand is I have yet to finish grading one of your exams. The rest of you should have an exam score already from that first exam, and I believe I put into the assignment the I think you can get into it now. I could be wrong, but I think I set it up so that way, as of recently, you can just click your way back into the exam, and at the very top of the assignment, it says, "Hey, here are the answers." And you can look and see what I put down as a set of answers. And in some cases, I'll just say that your answer was good, but if you're very imprecise in your wording and your words are ambiguous, or if mathematically you did something just a hair off, I tried to spot those things and give you appropriate partial credit. And I always love it when students, how do I phrase this? Argue for points. I actually don't really love it at all when students argue for points like they're like all feisty and chock full of attitude. But I do appreciate it when students say, "Hey, here's what I wrote. Here's what you said the right answer is. Here, I talked to a buddy, and here's what my buddy said, and here's why my answer, what I wrote, is actually really close to what you said a good and correct answer is. Could you help me understand why I got the partial credit that I did?" Because that either means you're understanding something and maybe I made a mistake in the grading, in which case I should fix it, or you're not understanding something and you don't understand that you don't yet understand. So it gives us the opportunity to talk through how your answer that's got some partial credit maybe could have been a little bit better. Sort of like sometimes students will, for example, use the word precision when they mean accuracy, or accuracy when they mean precision. Little things that don't occur at first, but they're tied to the definitions in our discipline. And so it's important to get them right. And usually that's where like a 1 point difference or a 2 point difference could be found. So definitely think it over. Definitely look at your questions and then the way you answered them, and then what I say a good set of answers should be. Second thing is, as of this week, for any lab activities or for all lab activities for the rest of the term, I've set up a new set of lab groups, and I have not been in a student position signing myself up to be in a lab group. And so I just trust that y'all are able to do it. I know past classes have been able to sort of get themselves into lab groups appropriate, but you know who you work well with a little bit. You know who you have time conflicts with versus, oh yeah, we're free at the same time. And so I've set up lab groups so that way you can jump into them yourself. And if you have any questions about how I, comma, student can do that. If you and everyone in your group is like, I don't know how to do it, just send me an email copying everyone in your group saying, okay, here's the group of the five of us, or perhaps a group of four of us that want to work together. And just tell me all of the names, copy everyone on it, and I could assign you to be in a particular lab group. Again, if you can't figure it out, I can help you with that. So that's something I'd want to do. So that's administrative stuff. I don't have any other administrative announcements, but you might have some questions related to something administrative. Any administrative questions? Okay. How about question? Oh, and about those, arguments with the instructor about the partial credit. What I usually like to do is to say, let's not worry about it the day that I return an exam. Like if I get a bunch of you showing up in office hours, that's like a drag, especially if you're all fussy. But no, I think it's a good idea to, again, check with the buddy, make sure you have the good argument, put your best foot forward. Send me an email explaining the situation, like, hey, on this problem, I got partial credit. I got 3 out of 5. I think I should have got 5 out of 5. Here's the answer I put, do a little screenshot, put the answer in there. Here's what the answer you wrote is. And then I could say, hey, this is best for talking about in office hours, or let's set up a Zoom meeting. Or I could say, this is something I think is pretty quick by email, and I'll reply via email. But yeah, sort of put it in the form of an email, your best argument for why you should get more points, and we'll move forward from there. But don't just show up in office hours and ambush me. Actually, that's okay. I don't mind that, but it's you're more likely to get more points when you put your best foot forward and have a solid argument for more points, and put it in sort of a place where I can sort of consider it and I don't feel rushed. Okay. Then also, I guess you have either homework and or a lab that are due soon related to material from regression. Any questions about that before we pick up with chapter 4?
If I understood correctly, we're being put into new lab groups. Are these on Canvas?
Yeah,
Or are
in
we adding to
Canvas,
this?
and you sign up for it yourself. I mean, there's a
Oh, okay.
thing at my end where I could say, allow students to sign up for the lab groups themselves, and I check that box.
Okay.
And in past classes, that's always worked out. But there's always a couple of students who are like, I don't know how to do this. And I can sort of do that for you, again, if you send me an email. But you can sort of work together starting right after class, whenever is convenient for you and your groups. And so I'd recommend reaching out to the people that you've either been in groups with in the past and it's worked out well, or people that are time-wise matching up. And so that way, by the time we get to, like 1:30 or 2 p.m., you're all happy with a group of 4 or 5. And just be prepared to add another person if I know, like, when you sign up for a lab group and you let me know, hey, here's when our group is meeting. That's something you can sort of do, and someone might need a lab group, and if I find out when y'all are meeting and they're free when you are, maybe they'll be added in, something like that. Okay, does that answer your question, Claire?
Yeah, thank you.
Cool. Anyone want to follow up on that? Okay, any questions on anything related to the past, regression most recently, or correlation right before that? Okay, so let's share a screen and dive in on something new. And today I think is conceptually easy, but we need to get some terms defined so we can move forward as a group and understand a couple key concepts. And today we're going to talk about in class sampling, methods of sampling. Two in particular will sort of be prominent. Then we'll talk about how to perform an experiment where you are not sampling, but rather assigning individuals to a treatment. But I'm not going to have that experimental design be part of our lab activity today. That's going to be better matched up to a later lab where we talk about analysis of variance, one of the other methods that we're going to sort of go into. So a little bit later is when we're going to sort of do a lab that talks about experimental design. But for today, it's going to be sampling, and then we're going to sort of close off with concepts of bias and precision. Okay, so let's just jump right in with sampling. And the idea that we have, and I think we expressed this earlier, is you got a population out there. The population is of size capital N, and just to make sure it's like clear, maybe I'll write it that way. Oh my gosh, that looks like a weird mu. I'll just say capital N is the size of your population, okay? And the population, think individuals out there in this group, okay? So this could be citizens of California. It could be people who live in San Luis Obispo. It could be a process instead of a population, but something like, if I were to set the dials at these particular locations on my machine that produces Cheetos, and yes, if you're like no food science majors, they'll say, oh yeah, we got one of those. And it's cool machine. And you just set these dials to various levels and you put stuff in the top in the hopper and pour water in the water receptacle and you get Cheetos out at the other end. But if you put different stuff in there, it will extrude something like oatmeal, okay, that you could then freeze dry, okay? So they got this process, okay, and instead of a population per se, we could talk about a process for creating something. Like we're gonna, make alloys, okay, and mix two metals at a certain mixing rate. Okay, so there's a population out there, or there's a process, and we have information about that population. Maybe it's going to be a population mean mu, a population standard deviation sigma, maybe even information about a population histogram. We could measure the skewness in some way. Our book talks about a numeric measure of skewness. It doesn't play a huge role, but maybe in your discipline, you sort of care about the measure of skewness. How skewed is it? And so there's a population histogram, population characteristics that are numerically summarized. They're just a way of describing the individuals in that population, or the individuals that could be the result of a particular process. So we've got a process now of sampling from that population, and literally you're going to sample N of the capital N individuals, okay, from the population. And I guess if we have a process, there might not be a capital N, but it's like we set the cheese doodle Cheeto, the Cheeto machine to, again, a set of collection of particular settings, and it could just keep creating this new product, this food product, over and over and over again. And instead of a finite number of individuals, we could just keep running it forever. Okay, so I'm just saying you're sampling N individuals from the collection of possible individuals. And there's a couple methods of sampling. The methods that I'll talk about are haphazard. And that's one thing that the lab asks you to do. And let's be really clear about it. If I'm saying pick a sample that seems good to you by eye, do it that way. Just do your best to come up with a method that will fairly capture the characteristics of the population in your sample. Because when we get a sample, you might very well get an average from the sample or a standard deviation from the sample. And the belief is somehow that those are reflecting the population characteristics. Okay, so you want to sort of have your sample be representative of that greater population. And you think, hey, I could do that by eye. I could come up with a method that seems easy. Okay, haphazard samples usually have the benefit of being easy to work with. Okay, simple random sample. SRS for simple random sample. Okay, a simple random sample of size lowercase n. Okay, from the capital N individuals. Okay, so yeah, literally, we're going to sample lowercase n from the capital N individuals. Is defined the following way. Every sample of lowercase n from the possible capital N, you're thinking capital N choose lowercase n, okay? That's the number of ways of doing it. Every one of those is equally likely. Okay, so every possible sample of, say, 6 of the 33 of you is equally likely. Now, that is sort of easy to grab onto, but I'm thinking there's a lot of possible samples. So yeah, 33 individuals choose 6. Okay, that'd be 33 factorial over 6 factorial, then 33 minus 6 factorial. That's a lot of possible samples. So it's like 33 times 32 times 31 times 30 times 29 times 28 times 28, and then divide that through by 6 times 5, 4, 3, 2, and then 1. That is a very large number of possible samples, and each and every one of those samples has to be equally likely to be the one that we see. Okay, so that's our definition. But that implies something that I think most people would say, oh yeah, I know that that means fair. Okay, so that means every individual is just as likely to be sampled as every other individual. Literally, if every person is equally likely to be in the sample as every other person, that is almost, but not quite, a simple random sample. But ask yourself this: when either designing an experiment or when looking at a description of how data were collected, okay, the question is, do we have every individual who could be sampled just as likely to be in the sample as every other individual? That would be a simple random sample. Every individual is equally likely to be in the sample. Okay, so they're in the sample. Okay, so that's worth saving. Okay, any questions about that so far? Okay, it's clear and move on. Okay, so I'm going to tell you a quick benefit of simple random sampling or randomness in the sampling. Every single equation in our textbook from here on out corresponds to, we assume that there was some randomness involved in the sampling of the individuals from the population. Or we assume, like later in class today, we assume the individuals were randomly assigned to a particular treatment, like a medical treatment. You either get the control or the actual real treatment, and we flipped a coin to determine who's in which group. Okay, so to sort of use any of the statistical methods from here on out, we have to have some story that involves randomness. We have no stories that involve haphazard sampling. Okay, and so if someone says we're collecting our data via this haphazard method, okay, you have to ask yourself, are some individuals more likely to have been in the sample than others, in which case there's maybe a bias of one sort or another. And secondarily, you have to say to yourself, if you did sample in a way that didn't involve actual true randomness, like rolling dice, then you're in a situation where the methods we're going to suggest won't necessarily apply at all. And if you use the method, it's like using a Phillips screwdriver when really you have a flathead screw. Can you do it? I guess if you're really careful and put it at an angle, you might be able to get lucky. But the methods match the sampling procedure. And so you really have to know how the data were collected to fairly analyze the data. I'm the statistical consultant for the second half of the summer, and I've got people coming by on a regular basis, meeting me via Zoom, saying, okay, here's how I got my data. Here's what I want to do. Here are the sort of questions I'd like to answer with my data. Can I? And sometimes I have to say, I'm sorry, you sampled how? I don't actually say it rudely like that. But I have to say, how did you actually collect your data? And if they tell me a method where I can't imagine any form of randomness, I'm pretty blunt and I say, well, how did you randomly sample? from that population? Or how do you randomly assign people to a treatment, like in an experiment? And if they can't tell me randomness, I have to sort of back off and say, well, what I'm about to tell you only really works, guaranteed, if you have a story of randomness, and you're just telling me you don't. So I can't guarantee that what I'm about to tell you will actually work the way it should. The tool I'm about to give to you might actually be the wrong tool for your question and your data. And so, hey, you want to go back and start over again, I'm happy to help you shoehorn your data into a story, and I'm happy to do my best to help you redesign your analysis and data gathering method, but we got to do it right. Okay, so simple random sampling is the gold standard. There are a variety of other methods of sampling, multi-stage cluster sampling, fancy methods. Our book only mentions one other that I really would like to draw to your attention, and that is called stratified sampling. And the lab walks you through an example of dealing with stratified sampling. And in stratified sampling, your whole population out there, and I'm assuming you've got an actual physical population here, stratified sampling doesn't really work in the context of the process, but rather only a population. So you've got these individuals in the population, okay? And you can lump them into groups that are in some fashion cohesive, okay? They're a natural group, okay? Those, and maybe those. So you've got maybe these 5 different strata, okay? There's and I'm not saying low, medium, and high. I'm just saying there's these different groups, okay, that seem sort of natural in the context of, Cal Poly and sometimes class projects. You're asked to go sample students or, ask people at random a questionnaire. Well, I'm thinking you have folks out there who are in the engineering, and then there's ag folks, cafes, College of Agriculture, Food, Environmental, I don't know, cafes. There's COSAM, BCSM, CLA. There's 2 other colleges, OCOB, but let's lump them in with engineering, architecture. So you might have 5 different strata because you think there's a different rate of occurrence of some characteristic across the different colleges. Or perhaps students have a different sort of natural tendency to be lumped in these categories, okay? So the strata correspond to groups that make sense. And within each stratum, okay, you might have a mu. Mu1, Mu2, all the way up through, in this case, Mu5 in general, maybe up through Mu K. There could be a Sigma 1, Sigma 2, up through Sigma K. And you would love to know characteristics separately within each of the strata. Okay, an example of the sort of thing that Cal Poly as an institution cares about is what is the rate of students who need to repeat a class? Okay, is the rate of needing to repeat a class the same across the different colleges, or is it different between the different colleges? And so you would want to know maybe the rate of repeating, and that could be P1 and P2 and P up through P5. You'd like to know these different proportions, okay? And within the strata, there may be differences, but I know that if I sample at random via a simple random sampling method, because there are so few people in architecture, 5% of Cal Poly students are like from the College of Arch, I might miss, in a sample of 20 students, I might miss all of the architect folks. I might get no one from the College of Architecture if I sampled only 20. I'll probably get like 6 engineers, but if I have no one from the College of Architecture, I'm not going to be able to fairly assess what's going on in some colleges. So stratified sampling is usually going to happen when you'd like to know information about each and every one of the strata separately. You might very well oversample within architecture and undersample within engineering. If I can get a sample of 5 students from each of the different colleges, That might not be a huge sample, but at least I would have someone from each of the different colleges. So from our different strata, we could take different samples. We could have a sample of N1 from engineering, N2 from cafes, all the way up through N5 from CLA. And there's a collection of these different N's. And I guess from each sample, I could get a Y bar from the sample and a standard deviation from the sample. So Y bar 2 and S2, Y bar 5, S5 could be obtained. Okay. And if I'm sampling with a different rate of sampling to come up with an estimate of the overall mean across all of the different groups. So again, there's one overall mean. Okay, so mu is the mean of everybody taken together. I would want to estimate a number of mu. I'm going to call it maybe mu hat. And that could be done with a weighted average of our sample means. Okay, so yeah, literally, if the stratum sizes are known, like you have N1 individuals, okay, N2 individuals, all the way up through N5 or NK in general individuals, mu hat, my estimate of the mean overall could be a weighted average of the individual group means. So N1 over capital N, that's the rate of occurrence in that first stratum. So capital N1 of N is the first stratum's weight. And I'm going to take Y bar for that first mean. And so my rate overall is a number in the range 0 up to 1. That's a rate multiplied by its Y bar plus N2 over capital N times Y bar 2 plus all the way up through capital NK over capital N of Y bar from that kth group. So that weighted average of my separate stratum or separate strata individual means, I've got information about each of the different strata, that will allow me to come up with an estimate of the mean overall, or maybe the proportion of students overall that need to repeat a class across all Cal Poly. I mean, even if in the different colleges you have different rates of needing to repeat a class, okay, there is an overall average. And if I sample in this stratified way, so I can get averages from each of the different groups, averages that are based on reasonable enough sample sizes from each of the different groups, I could then overall scale it up until I have a good estimate of the overall population mean. Any questions about that so far? Okay. Okay, so actually I'm not going to talk about cluster sampling, but I'm going to say it's sort of a fun read in our book about cluster sampling. So I'm going to encourage you to read that as well. Let's talk about experiments where we need to literally randomly assign a treatment to an individual. So random assignment. I've got a collection of individuals that are willing to participate in the study, okay? Or maybe I'm making alloy. And so, you know, across my my 9 different ways of making this alloy, so sort of 9 different methods. Think zinc and copper, okay? So I'm going to mix zinc and copper in 9 different ways, okay? And how would I randomly assign individuals, okay, to the in this experiment? Well, I don't really assign individuals, but I have to fairly I have to fairly construct this. And if in the process, the course of one day, I can make these 9 chunks of metal via these 9 different methods of making this alloy, where I'm going to later assess the hardness of each of the alloys. Okay, maybe earlier in the day, I'm not going to be as good at sort of blending the 2 metals together. And maybe by the time the day ends, I'm going to get quite a bit better. And so you'd think that earlier in the day, there might be a systematic tendency to be a little bit different than later in the day in terms of the ultimate hardness of the metal that I'm creating. Okay. And so maybe across the 9 different methods, I'm going to have to put them in a particular order: the first run, the second, the third. I have to randomly assign the 9 different methods to the run number. Okay, so the run number could be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So across the 9 different methods, I'm going to, again, with a completely randomized design, sometimes termed a CRD. Okay, I'm going to choose the right number of individuals to receive each treatment, the right number of individuals from the runs, okay, to receive each of these different treatments. Okay, so I'm going to choose, and this is the general way of doing this, choose N1 to receive treatment 1, TTT for treatment 1, and 2 to receive treatment 2, all the way up through N K to receive treatment K. So because I've got exactly 9 times that I'm going to be doing this experiment, okay, and I've got 9 different methods out there, I'm going to choose 1 to be receiving treatment 1. So of my 9 different methods, I'm going to call them maybe A, B, C, D, E, F, G, H, and I. Okay. And I'm going to pick for treatment A, I'm going to choose just one of these 9 ways, or one of these 9 orders to receive treatment A. So I'm just roll dice. I rolled dice, I got a 4. And so treatment A at random was going to be the 4th thing that I do. Okay. And then let's go for B. Well, I'm going to roll dice again. I'm going to roll my 9-sided die. And if you don't know about 9-sided dice, I'd encourage you to consider a 20-sided die. And let's just assume it's a fair die. And if I roll a 4 again, I'm thinking, oh, well, I've already got the 4th slot. The 4th run is going to be receiving treatment A. I need to simply re-roll. And so I re-roll and I get a 7. So B receives 7. And I have to find now for treatment C, what treatment is it going to get? And I roll the dice and I get a 2. So that gets C. And we eventually take each of these 9 different methods and slot them into a particular run. Okay. So what if we have the concept of replication? Oh, any questions before I talk about replication? Okay, so replication means the number of individuals that receive each treatment. So if N2 were 2 and N3 were 2, all the way up through, in this case, N9, if it's also going to be 2, I might have, again, I'm going to have 2 treatments, or 2 occurrences of every treatment across my now 18 runs. So if we have the runs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. And again, I have the same experimental treatments before as A, B, C, D, E, F, G, H, and I. If I was using a CRD, okay, and I've got these 2 replicates of each treatment, okay, if N1 is 2, I'm going to choose 2 of the 18 to receive treatment A. So I might, I'm going to roll my 18-sided die, okay? Or if you have a 20-sided die, use that one. Fine. You're going to get treatment A on 8 because you got an 8, and then also a 4. So you pick up your die again, and you're saying, now I'm going to sort of randomly assign who gets treatment B, and you get N8 again. So you say, well, I already, 8, already got A. So I'm going to roll again. I get a 16, and that's B, and I get a 14, also B, etc. Until we have N1, 2 occurrences of A, N2 is 2 occurrences of B, all the way up through N9 is 2 occurrences of I. Okay. So we're going to choose 2 individuals from each group, or 2 treatments, 2 occurrences for each of the treatments. 2 individual chunks of metal will be created. Or maybe if it's people in a class, okay, 18 students in a class, I could choose 2 of you to receive form of the test A. The test form C could be received by 2 individuals, etc. You could again randomly assign individuals to the particular different treatments. Okay. Just a quick note, there is no obligation that all of the group or the number of individuals, the number of replicates for each of the different treatments be the same. N1, 2, 3 up through NK do not need to be the same. If they are the same, we would say the design is balanced, and there are some real benefits of having a balanced design. Okay. Now, any questions before I move forward just a hair? Okay. Let's talk about blocking, okay? And blocking is if you have another factor besides perhaps your main treatment factor that you think may have an impact on the results, you would want to do blocking. Okay, so let's talk about, again, making an alloy, and we'll talk about 3 different methods for making the alloy. And again, what is it, aluminum and, copper and zinc. And so we could have mixing rates of 60%, 65%, and 70% for the copper. And then the zinc would be then, I guess, 40, 35, and 30%. So the amount of copper and zinc. Okay. And so we have either the 60-40 blend, the 65-35 blend, or the 70-30 blend. And well, when you're doing your creation of the alloy, you mix these metals in molten state, and you have 3 different furnace settings. And the furnace settings could be my blocking variable. There's the low temperature, the medium temperature, and the high temperature of my furnace. Okay. No, so the low temperature, it's going to be enough to melt both. Okay. And you mix it up. The medium temperature is considerably warmer. It's 10 degrees centigrade higher. The high temperature is even warmer than that, another 10 degrees centigrade higher than the minimum melting and blending point. Okay. And it's entirely possible in my mind that the different temperature could have an impact on the hardness of the alloy that's created. I'm going to bet not, because it's copper and zinc, and those are 2 different metals with 2 different hardnesses. Probably it's the metal itself that has the larger impact, but it's possible that the temperature at which I do the blending will have an impact on the results. So I'd like to block on that variable. A way that we could do that is to put our temperatures, low, medium, and high, okay, into as columns in a matrix. And I could have my 60-40 blend, my 65 or my 75% copper blend, okay? And across my 9 different treatment slots, the run order, the first, second, third, fourth, fifth, I could randomly assign them to which of these 9 different locations. Again, 3 different treatments, and then the different blocking variable. Okay, so 3 different treatment levels, it's the mixing rate. And so maybe of these 9 possibilities, maybe it's the first one is going to be there, and then the second and third, fourth, etc. And we could fill in which of the treatments is first, second, third, all the way through the very end. And if you want to think about it, so what if you got these 18 because you want to do 2 replications? Well, just do it twice. We're all good. Okay. So let's move forward just a little bit into chapter 4, section 4, which is, I think, the coolest thing out there. And it's considering how our process of sampling has an impact on the result. Okay, chapter 4, section 4. If our population out there has maybe a histogram of values, and maybe I care about a number that I'll call theta. Theta values of interest might be the mean, it could be the standard deviation or the variance, it could be even the 40th percentile. Just some numeric summary of the population. There's a numeric summary out there for the population for whatever population you have and whatever way you would like to summarize it. Maybe you care about the 95th percentile of some population of hardnesses or something like that. I don't know. But we're going to take a sample size lowercase n from that population, and I'm going to come up with a theta hat, an estimator. So estimate is like the number itself. The estimator is the procedure. It's a way of coming up with a theta hat. And maybe, you know, your sample mean could be your way of estimating mu. So if the number you'd like to estimate is mu, the population mean, you're going to use your theta hat will correspond to your sample mean x bar. Okay, so theta out there is the truth. Okay, and theta hat is your estimator. And here's and I'm going to switch gears a little bit into a slightly new notation that we didn't use last week, but I'm going to say the expected value of theta hat. You might last week have called that mu of theta hat. So the expected value of theta hat is just the mean of the possible theta hat values. Your way of randomly sampling n individuals will give you maybe a different collection of possible x bars. Some of your x bars are low, some of your x bars are high. On average, what is your value of x bar? What is mu of the x bars? Okay. The expected value of theta hat minus the true value of theta is going to be just termed the bias of your estimator theta hat. Okay, it tells you how far off you are on average. Here's on average what you would say based on the data. Here's the truth. How far off is the average of our numeric answer from the true number we're trying to grab onto? Another interesting question is the variance of our estimator, okay? The variance of your estimator, if you will, or if you want to call it sigma hat squared of the theta hat, okay? That's your variance. Okay, it tells us how close our theta hat tends to be to the actual theta. So let me show you maybe a picture of a biased estimator and then an unbiased estimator, okay, and then with a low and then with a high variance, okay? So if we have an estimator that the histogram of our theta hats, if the histogram of the theta hats is centered at theta, okay, this would be unbiased because the expected value of the theta hats, you know, sort of over the different possible theta hats. Sometimes, again, sometimes theta hat is a lot larger than theta. Sometimes it's a lot smaller than theta, but on average, okay, here we have unbiased. The expected value of the theta hat is just theta. Here's an example of a biased estimator. So maybe here's the true theta, but hey, check this one out. On average of our theta hats that could occur, they average out to right around here. Here's the expected value of the theta hat. And this difference, horizontal difference between the actual theta and the expected value of theta hat, this is going to be our bias of theta hat. How far off are you? Well, on average, we're low. I'm sorry, in this case, on average, your estimator is above the truth. Okay. On the other hand, this guy is, while unbiased, there's a large degree of variability, imprecise. Here we've got quite precise. Precise would be low variance. Here we've got high variance. There's a lot of variability in the possible theta hats versus not so much variability in the theta hats. So of these two situations, which would you prefer? Well, that's a really tough question because I don't know that either is the one I want, but if these are my two options that I have to work with, I can either say, I'm going to choose to go with something that's unbiased, but heck, I could be all over the map, or I could choose something that's biased, but I know I'm never too far away from the truth. Even though on average I'm not at the truth, I'm never too far away from it. In this situation, we would recommend something called mean square error as a way of MSE for mean square error. Mean square error is a way of comparing our different possible estimators. The mean square error is equal to the typical value of, or the expected value of, theta hat minus the actual theta squared. Okay, and that happens to mathematically equal the variance, or better yet, the bias squared of your theta hat, plus then the variance of your theta hat. Okay, and so I'm thinking the smallest mean square error says, well, our estimate theta hat minus the actual truth, that difference squared, we would love mean square error to be small. The method that's better is the one with the smaller mean square error. And if you have two methods that are both unbiased, they both have a 0 in that first slot. And so it's the smaller variance will have the smaller mean square error. If, on the other hand, you have one of the methods that's biased, if the bias is small and its variance is tiny, between the two of them added up, you might have something that's better. And this is something the lab walks you into and through. Yeah, literally in the lab, you're going to estimate the bias. So the bias in a sample, the bias estimate, okay, is going to be your average. Hold on, do I want to do it this way? No, don't want to do it in that way. I'm going to restate that just a little bit. I'm sorry about that. Let's erase and move forward. If I have values and an estimate of the average, so the average X bar of the theta hats, okay, and I've got a standard deviation of the theta hats, and if I know mu out there, I'm sorry, if I know theta, so if theta is known, and that's something like a population proportion or a population mean, okay, I'm going to have the mean square error, MSE, from my data is corresponding to X bar of the theta hats minus theta, that's the bias, square that, plus then the standard deviation of the theta hats squared. Again, the variance is just the standard deviation squared, and then the bias, well, we're going to have to take that bias and square it. And so in the lab, we're walking you through a situation where you're going to have to determine a way of estimating a proportion. there is a truth out there, a true value, and then there's sample-based values. There's a true rate of occurrence, and I'm going to call that P. And then you've got P1, P2, etc., a collection of different. Hold on a second. You've got the average of your various values, the P's. You're going to have P bar, and then you're going to have a standard deviation of the P's as well. So just take that standard deviation square and compare your average to the truth, and then square that difference. And that would be a way of estimating the mean square error. How well does your estimation procedure do? Okay, so that's a lot of content, and it's time to sort of stop sharing the screen because it's about 1 o'clock, and it's time for me to also stop recording. But you're welcome to leave now if you got it. That's fine. That's cool. Do any of you have questions that maybe you'd want to ask before I stop the recording? Okay, so where you stand is, yes, get into a group, a lab group. You've probably reached out already, or shortly you should reach out to those that you've worked well with in the lab in the recent past and said, hey, you want to be in a lab group again? And most likely the answer is going to be yes, or maybe, well, I wish you had asked earlier because I've just agreed with these other people. Figure it out, figure out which group you're going to be in, sign up for those groups jointly together. And if you have any problems with that or any difficulty, send me an email with all 5 names or possibly 4 names if you can only find 4 people total. And I will stick you into a lab group. I could do it for you if you need to, but I have confidence that you can figure it out yourself. So enjoy the next time period in your life, and we'll see you perhaps in office hours at about 5:10. Otherwise, have a good afternoon. Bye-bye.